Hi roboticist! Today what we are going to do is to spawn our 6-axis robot in Gazebo, where the physics takes part in our 3D simulation. Before diving into it, make sure to subscribe to the channel and give a thumbs up for more topics on learning ROS. In the last video, we have learned how to simplify our URDF file using xacro file, where you put a macro for describing links and joints in a standardized way, let's say. What we have done so far is to visualize the robot only in RVs, and it has nothing to do with the physics of our environment, so the gravity or other external forces are not applied in RVs. If we want to put the physics in our simulation, it is necessary to update every link with inertia values. Inertia values are components of a tensor that describes how the mass of a component, in this case a cylinder, is distributed around the center of rotation, or the axis of rotation, let's say. Generally speaking, the more mass you have away from the center of rotation, the more that component has a greater inertia. In the ROS wiki page, you can find a deeper explanation about that, and you can visit the list of the moments of inertia in Wikipedia, where you can take the formula for calculating these 6 values depending on the type of the components, or better, the link and the axis of rotation. We have modeled our robots in terms of cylinders and box for the TCP connector. And in the Wikipedia page, we can calculate these 6 values of inertia depending on where the center of rotation is applied, at the center or at the end, or as for example for the link 1 at the longitudinal axis of our cylinder. So it's just a matter of detecting what is the radius and the length, and makes this calculation reconducting the type of movement, or better, the rotation that we have in our model. And for example, in the link 1 we have the rotation that corresponds to the axis of the cylinder, and in all other links we can reconduct the center of rotation at the end of the cylinder itself. So, after this background, we can put our inertia value, or better, structure our link with the inertia tag in our xacro file, because this is something that every link has to have. So instead of modifying the URDF file and repeat all these inertia tags for all the links, we can modify only our xacro file, or better, our joint underscore link xacro file. Okay, and inside the link tag of our macro, we can add our inertial tag, where we're gonna put our origin in x, y, z, and the origin in row, pitch, and yaw, that is going to be the same of the center of the collision and the visual. and we need to put the mass and all the inertia value, and we're going to use the formula of the wiki page for simplification. Okay, don't worry about the inertia value, because usually these values are provided from mechanical designing engineering, because in SolidWorks, for example, with 3D design software for mechanical designs, it's very easy to calculate the inertia value, because it had every software has an embedded calculation algorithm to provide the inertia value. But for this tutorial we are gonna use and we are gonna calculate the inertia value from the formula and wiki page. That's why we have modeled our links in such a way that are reconducted to a cylinder, and with a center of rotation that could be at the longitudinal axis for example for the link 1, and for the other links the center of rotation is gonna be at the edge for simplicity of the cylinder itself. So you're gonna use the solid cylinder formula, and now it's just a matter to take the length as the h of the formula and the radius as r. And if you do the math, you are gonna calculate the value that I'm putting right now. So feel free to challenge these numbers. I put a mass of 1, this is gonna be 1 kilo, and so on and so forth. So we are gonna do the same calculation for the base link and the link 1 as well. Then we're gonna do the calculation for the link 2, which in this case is a cylinder with the center of rotation that is in the edge. So it has the value, only the value in the diagonal, with the exception of the yy that is gonna be 0. So we just need to adapt our calculation with our new values. We have considered this cylinder to have a mass of 2 kilos. And again, if you do the math, you're gonna reach the same values. Again, feel free to challenge these numbers and with a different value for the mass. So I hope that you got the point and how to proceed forward. So you can do the same for the link 3 and link 4 as well. I put with the link 3 in a link 3 a mass of 2, and so it's gonna be the same value, because in both In link 3 it has the center of rotation that is on the edge, and the same things or same concept, let's say, for the link 4. And the same for the link 5, with the changing of only the mass value. Okay, we have put our inertial value in our links, or better, cylinder links that are the body of our robots, and then we need to think about the inertial values of our TCP connector that we have modeled as a box. So we just need to keep the formula for inertia values that has the center of rotation at the center of the box itself. So it is a matter to put a numerical value in the variable W, H and D, and you are gonna arrive to the value of inertia that I have retrieved. So again, feel free to challenge this number. And we are gonna do the same things for the gripper, left and right. In the gripper, we are not going to rotate because it's not going to be a rotation, but we could keep this number for simplification. And now what we need to do is to create a launch file to spawn our robot in an empty world that, or better, in a gazebo world that, remember you, that has its own physics. So there's gonna be the gravity. So first of all, we need to assign a URDF file to our robot description parameter, because it is a parameter that reads a URDF file. And then we need to set as an argument the position where the robot is going to be spawned. And we are going to set in X, Y, Z 0, 0, 0 for simplicity, because it is just an empty world. And now we need to launch the gazebo world, or better, the empty world, in a paused mode. Why paused? This is something that you will see in a moment. So we need to include the empty world.launch file that is belonging to the Gazebo ROS package embedded in your Noetic version of ROS. And then we need to put as an argument the use sim time, the bug, the GUI, and here we are gonna put as an argument post value true. So when we are gonna launch our Gazebo simulation, the Gazebo simulation will be on pause, and to go live we will need to press the button play. So imagine that now we have our robot description charged, or better load with our URDF file. We have decided where the robot needs to be spawned. We have launched our empty world Gazebo world, and then we have everything to spawn our robot in our empty world. So we need to use for that the node we are gonna call spawn the robots, and the node is belonging to the package gazebo underscore ROS, and the executable file will be spawn model, and we're gonna put output screen, and as arguments we are gonna pass the value in x, y, z where we want the robot to be spawned, as well as the robot description parameters. Okay, we have created our launch file that's gonna call spawn robots, and we can test it by typing ROS launch, the name of the package, and the launch file spawn underscore robot dot launch, and see what's happened. Okay, this is an error that came up due to the ROS snippet. It's not a problem, so let's correct it right away and check it again. Okay, nice. As you can see, our cobot, our 6-axis robot, is correctly spawned in our empty world in Gazebo, and it is centered in the x0, y0 and z0, and it's gonna be really pretty. Okay, so as I said, our world is in pause, and you can see that the robot is spawned and it is straight with every joint that are in the default position, which is gonna be 0, 0, 0. Okay, and then what's happened if we press play? So let's do it and see what's happened. You can see that the robot is falling down. Okay, why that? Well, this is going to happen because we have our inertial value, so all the links are affected to the gravity, and we don't have any control on that. So that's why we need to put for each joint a controller in such a way that the joint can overcome the force of gravity, avoiding the robot falls down. So this is the topic of the next series of video, where we are going to talk deeply on ROS control, where for each joint we are gonna put the transmission tag, the Gazebo plugin, and we are going to learn how to trick the PID control for each joint, which will be very interesting, I promise you. So that's all for today. I hope that you enjoyed this video. If you got a lot of technical value out from this video, make sure to subscribe to the channel and give a thumbs up, and don't hesitate to write in the comment down below if you faced any problem in replicating this model, or simply you want to adapt this method to your robot model. So again, thanks for your attention, and keep learning robotics with Ross.